Look up on a clear, moonless night, far from the glare of cities. You will see it. A faint, luminous band stretching across the heavens. A river of light that our ancestors saw as a pathway for souls. We know it today as the collective glow of billions of distant suns. This is our home, the Milky Way, seen from the inside out. For all of human history, this view has been our only perspective. We have been travelers on a ship, able to see our own vessel only from the confines of its deck. We could map the nearby stars, chart the clouds of gas, and infer the grand structure that contains us. But to truly see our galactic island in its entirety, to hold its spiraling form in our mind's eye, has been a feat of imagination, an artist's rendering, an educated guess. Until now, in the silent humming racks of a supercomputer, a new cosmos has flickered into existence. It is not a photograph, nor is it an artist's impression. This is a complete self-evolving replica of our home galaxy, a digital twin born from data and mathematics. A synthetic intelligence has meticulously constructed a virtual Milky Way not as a static image, but as a living, breathing system. It contains 100 billion individual points of light, each one a simulated star with its own mass, its own history, and its own unique dance around the galactic core. For the first time, we have not just imagined our home, we have built it. To comprehend the scale of this achievement is to grasp for superlatives. Simulating a galaxy is one of the most formidable challenges in all of computational science. It is a problem of staggering complexity, a celestial ballet with an almost infinite number of dancers. The universe is governed by a handful of fundamental forces, but their interplay across cosmic scales creates a tapestry of bewildering intricacy. Gravity, the grand architect, pulls everything together. It sculpts the vast, invisible scaffolds of dark matter that form the skeleton of our stellar metropolis. Within this ghostly framework, ordinary matter unfolds its own drama. Immense clouds of hydrogen gas, colder than anything on Earth, collapse under their own weight. Pockets of this interstellar medium grow dense, igniting into new suns. These celestial furnaces burn for millions or billions of years, fusing simple elements into the heavier materials of existence. When the most massive of these luminous orbs die, they explode. Supernovae detonate with the force of 1 billion trillion nuclear weapons, blasting heavy elements back into space. This violent feedback churns the galactic medium, seeding the next generation of stellar bodies and planets with the stuff of life. It is a cycle of creation and destruction, a cosmic ecosystem playing out over 13 billion years. Previous attempts to model this process were heroic, yet limited. They were like trying to paint the Mona Lisa with a house brush. Computational power was the primary bottleneck. Scientists had to make compromises. They could create a high-resolution simulation of a small patch of a galaxy, perhaps a single star-forming nebula, capturing the physics in exquisite detail. Alternatively, they could model an entire galactic structure, but only by smudging the details, treating entire clusters of stars as single blurry pixels. The individual suns, the very components of the grand design, were lost. Resolving each point of light in a system of 100,000 million was considered computationally impossible, a dream for a distant future. The obstacle was not just a matter of processing speed, it was a problem of sheer interaction. Each of the 100 billion stellar objects in our cosmic island pulls on every other one. Calculating this web of gravitational influence is an astronomical task, growing exponentially with the number of bodies involved. A brute force calculation would take the fastest computers we possess longer than the current age of the universe to complete. The dream of a one-to-one digital replica seemed destined to remain just that. A new kind of thinking was required. That new approach arrived from an entirely different field of science. It came from the study of artificial intelligence of neural networks designed to learn, recognize patterns, and make predictions. Scientists began to wonder, what if we didn't have to calculate everything? What if, instead, a machine could learn the fundamental rules of galactic evolution? Could a sufficiently advanced learning algorithm be taught the physics of the cosmos, not by memorizing equations, but by observing the results? The idea was to build a computational intelligence that could fill in the gaps, a synthetic mind that could infer the fine-grained details from the broad strokes. The process began by feeding the nascent AI an encyclopedic diet of cosmic information. It consumed data from decades of astronomical observation. The Gaia Space Observatory provided it with a precise 3D map of nearly 2 billion nearby stars, their positions and their velocities. This was the ground truth, the anchor to reality. The Hubble and James Webb Space Telescopes offered deep-field views, snapshots of distant galaxies in various stages of their lives, a cosmic photo album showing how structures like ours form and change. The cognitive engine absorbed all of it, learning the visual grammar of the universe. But static images were not enough. To understand evolution, the machine needed to see things in motion, so its creators showed it thousands of smaller conventional simulations. These were highly accurate physical models of limited areas like the collision of two gas clouds or the formation of a star cluster. The AI never saw the underlying equations. It simply watched the outcomes over and over again. Like a child learning to speak by listening, the neural network began to grasp the unspoken syntax of cosmic physics. It learned how gas behaves where stars tend to form, and how their collective gravity shapes the majestic spiral arms. It was learning to become a cosmic artist with physics as its muse. Then came the final audacious step. Researchers provided the fully trained intelligence with a set of initial conditions, a blueprint representing the early state of the Milky Way, a few 100 million years after the Big Bang. This initial state, derived from our observations of the cosmic microwave background, was coarse and simple. It was a vast, lumpy halo of dark matter with primordial gas settled within it. From this seed, the AI was given a single command: evolve. Project this system forward 13 billion years and show us what it becomes. Show us our home. What followed was not a calculation in the traditional sense. It was an act of computational creation. The system did not laboriously compute every single gravitational interaction. Instead, it used its learned knowledge to predict how the system should behave. It placed 100 billion stellar particles, each one representing a single sun or a small system, and moved them according to the rules it had inferred. It painted in the swirling arms of the interstellar medium. It ignited fusion engines in the densest regions. It triggered supernova feedback loops. A digital genesis unfolded, guided by an intelligence that had learned the artistry of the cosmos. The result, when it finally emerged from the machine, was breathtaking. On the screen was not just a galaxy, it was recognizably times our times galaxy. The simulation had independently produced a grand spiral structure with a prominent central bar of older, redder stars. It possessed the correct mass, the right rotation speed, and a stellar population that mirrored the one we observe. From the wispy, star-starved outer halo to the chaotic, brilliant core, the virtual construct was a startlingly accurate reflection of reality. This digital Milky Way was not just a static portrait, it was a dynamic, functioning model of our home in the universe. With this unprecedented tool in hand, astronomers could finally explore our galaxy in ways that were previously impossible. They could fly through the simulated spiral arms, watching the intricate dance of gas clouds and newborn star clusters. They could dive into the galactic center where millions of suns orbit the supermassive black hole Sagittarius A times in a frantic, crowded ballet. The model was a laboratory, a time machine, and a telescope all in one. It allowed scientists to ask questions that observation alone could never answer. The cosmic mirror was ready to reveal its secrets. One of the first great mysteries this digital twin helped to unravel was the violent history of our galaxy's formation. Astronomers have long known that large galaxies like the Milky Way grew by consuming smaller ones. They are cosmic cannibals built from the shredded remains of their victims. In the real sky, we can see evidence of this past in the form of stellar streams, ghostly rivers of stars that trace the dying orbits of dwarf galaxies torn apart by our own galaxy's immense gravity. But these streams are faint and often hidden behind dense veils of dust. Connecting them and tracing them back to a single event is immensely difficult. Within the simulated universe, however, there is no dust to block the view. Researchers could watch these ancient mergers as they happened. They witnessed small satellite galaxies falling into the Milky Way's gravitational well, their forms stretched and unraveled like taffy. The model showed with stunning clarity how these captured stars disperse and form the faint, arcing structures we struggle to piece together from observation. By matching the simulated streams to the real ones, scientists can now rewind the clock with confidence. They can identify the specific ancestors of our modern galaxy, giving us a detailed family tree stretching back to the dawn of time. The new cosmic model also shed light on the engine at the heart of our home. The center of the Milky Way contains a dense, elongated structure of stars known as the galactic bar. For decades, there has been a debate about this feature. Is it a long-lasting, stable structure, or is it a temporary phenomenon? How does it affect the galaxy around it? Running the simulation forward, scientists could watch the bar form and evolve. The model demonstrated that this feature is a powerful and stable engine of galactic change. The bar rotates like a giant propeller in the center of the stellar disk, and its gravitational influence is profound. It acts as a cosmic funnel. It captures vast quantities of gas from the inner spiral arms and channels it inward toward the central supermassive black hole. This process explains how Sagittarius A times has been able to grow to its current mass of over 4 million suns. The simulation shows this river of inflowing gas in motion, revealing a dynamic plumbing system that feeds the monster at our galaxy's core. This provides a crucial link between the large-scale structure of the galaxy and the physics of its most mysterious central object. Perhaps most profoundly, the virtual Milky Way allows us to trace our own origin. Our sun is not a primordial star. It is a relative newcomer formed about 4.5 billion years ago. The iron in our blood, the calcium in our bones, the oxygen we breathe, all these heavy elements were forged inside an earlier generation of massive stars. These ancient suns lived fast and died young, seeding the cosmos with their remains. Our solar system was born from one such enriched cloud of gas and dust. But where did that material come from? Where has our solar system been on its long journey through the cosmos? The simulation offers a powerful new way to answer this question of cosmic provenance. By identifying a simulated star with the same age composition and orbital parameters as our own sun, researchers can trace its journey backward in time. The model reveals a likely history for our solar system. It shows our sun being born in a dense, chaotic star-forming region, a stellar nursery shared with thousands of siblings. Over billions of years, this birth cluster dissolved its members, cast out on their own separate orbits. The simulation then tracks our sun's winding path through the galactic spiral arms. It reveals periods spent passing through dense interstellar clouds, which may have triggered climatic changes on the early Earth. It also shows long, quiet stretches in the galactic suburbs, offering the stability needed for complex life to evolve. We can now watch a plausible history of our own journey through cosmic time, a 4-billion-year odyssey through danger and tranquility. The power of this new creation lies not just in its ability to replicate what we know, but in its potential to explore what we do not. It is a sandbox for the gods. Scientists can now run experiments that are physically impossible in the real universe. They can alter the fundamental parameters of the simulation to see how the galaxy would respond. What if the halo of dark matter were more concentrated or more diffuse? The model can show how this would change the shape of the spiral arms and the rate of star formation. It provides a direct way to test our theories about this mysterious invisible substance that makes up most of the universe's mass. We can ask even more profound questions. What would our stellar metropolis look like if the laws of star formation were slightly different? If supernovae returned less energy to their surroundings, would the galaxy become a calmer but ultimately less fertile place? By tweaking these variables, researchers can explore the vast parameter space of possible galaxies. This helps us understand why the Milky Way looks the way it does, and whether its properties are common or exceptionally rare in the cosmos. We can begin to understand our own galactic context, our place in the universal family of stellar systems. This digital twin is also a crystal ball. While it has been used to look back in time, its true power may lie in its ability to project the far future. Astronomers know that the Milky Way is on a collision course with our nearest large neighbor, the Andromeda Galaxy. This cosmic impact is inevitable, destined to occur in about 4.5 billion years. Past simulations of this event have been coarse, showing the two galaxies as blurry clouds of particles merging into one. With the new AI-driven model, we can witness this future cataclysm with terrifying and beautiful clarity. We can run the simulation forward, watching as Andromeda grows larger in our virtual sky. The model shows the first tentative tidal interactions as the outer halos of the two galaxies begin to intermingle. Then the primary encounter where the two great spirals pass through each other. Individual stars are unlikely to collide, so vast are the spaces between them, but their collective gravity will wreak havoc, throwing billions of suns into new chaotic orbits. Long streamers of stars and gas will be flung out into intergalactic space. The familiar spiral structures will be completely destroyed. After several passes and oscillations spanning hundreds of millions of years, the two systems will finally settle and merge. They will form a single giant elliptical galaxy, a new celestial entity dubbed Milky Way. For the first time, we can watch our ultimate fate unfold not as a cartoon but as a high-fidelity physical prediction. The creation of such a comprehensive and accurate mirror of reality inevitably leads to deeper, more philosophical questions. When a simulation becomes so good that it can independently generate the complex structures we see in the real universe, it forces us to re-examine the nature of reality itself. If the cosmos operates on a set of discoverable rules, and if a computational intelligence can learn those rules and use them to build a convincing facsimile, where does that leave us? It rekindles the age-old speculation: could our own universe be a simulation of some kind? This is not to say that the new model proves we live in a machine. It does not. But it makes the idea less a matter of pure fantasy and more a subject of serious, if speculative, thought. It demonstrates that complexity can emerge from underlying rules in a way that is computationally achievable. The universe we inhabit is, in a sense, a great computation. Matter and energy interact according to the laws of physics, processing information and evolving from one state to the next. What this new breakthrough shows is that we are finally beginning to build machines that can replicate that cosmic computation. Our simulation is a reflection of the universe's own inherent logic. We stand at a remarkable moment in our journey of discovery. The ancient view of a static, unknowable heavens has given way to a vision of a dynamic, evolving, and now a simulated cosmos. We have transcended the limitations of our physical viewpoint, stuck here in one small solar system on the edge of a spiral arm. A synthetic mind has given us a God's eye view, allowing us to hold our entire stellar home in the palm of our hand, to watch its history unfold and to glimpse its ultimate destiny. This achievement is more than just a technological milestone. It represents a fundamental shift in our relationship with the universe. The next time you stand under a dark night sky and you see that faint, shimmering band of light, remember what you are looking at. It is not just a collection of distant campfires in the dark. You are witnessing a snapshot of a vast, interconnected system, a city of 100 billion suns with a history of unimaginable violence and a future of spectacular transformation. And know that for the first time in a quiet server room somewhere on Earth, a perfect echo of that majestic river of light exists. A digital ghost, a mirror universe that is teaching us at last the true nature of our place in the cosmos. The silent conversation between reality and its reflection has just begun.